In several previous videos, we've looked at several different parts of the proton NMR spectrum. We've looked at how many signals there are and what that tells us about the molecule. We've looked at the chemical shift. We've looked at the integration, telling us how many protons give rise to each peak, and we've looked at the multiplicity. And what we're going to do now is put that all together and look at some examples of analyzing spectra with all of these tools that we have. Okay, so we want to propose a structure consistent with the following NMR spectrum. And so I think the first thing that's always good to do is to calculate the hydrogen deficiency index, right? And that'll tell us about how many double bonds and rings and things that we have, right? So to get the hydrogen deficiency index, we're going to take the number of carbons, right? So 10 times 2 plus 2. So to be saturated, we would need 22 carbon atoms. I'm sorry, we need 22 hydrogen atoms, right? But in fact, we have 14, right? So 22 minus 14, we're missing 8 hydrogens, right? So that gives us a hydrogen deficiency index of 4. Anytime you see a hydrogen deficiency index of 4 or greater, that's a pretty good clue that we've probably got a benzene ring in there, right? Because you've got the 3 double bonds and the ring. So that's a pretty high hydrogen deficiency index for a relatively small organic molecule, and so it's a good clue that we've probably got benzene. And when we look at the NMR spectrum, right, when we have peaks around 7 ppm, that's where we'd expect to see the aromatic hydrogens in that benzene ring. And even more specifically, we've got these 2 doublets, right? And so this is the pattern that we look for when we have a para-substituted benzene molecule. Right, so we've got groups coming off here and opposite. All right, so let's go to the next slide. We have a little bit more room. All right, so we're pretty sure we've got a para-substituted benzene molecule, and let's see what the other signals can tell us. So I have 2 more groups, right? And so these are probably the groups, right? I've got one above and one below. And I know I also have an oxygen, and I can see that the oxygen is not split, right? So that leads me to believe it's probably an OH. And then another pattern that I notice, when I have an integration signal of 9 that's a singlet, right, this is most likely a T-butyl group. And when I look, right, so my benzene's already taken up 1, 2, 3, 4, 5, 6 of the 10 carbons, right? My T-butyl group takes up the other 4, and so that's accounted for all of my carbons. So I think the most likely structure then is on one of the substituents, I have the T-butyl group, and then on the other substituent, I have the OH. And so I think the most likely structure is I have the T-butyl group and the OH. And I guess I should have said, right, when I identified this peak as an OH, right, it's also fairly far downfield, which is a good indication that I've probably got an OH, right? This is a little bit far downfield for a normal OH, but the fact that it's next to the benzene ring is going to shift it downfield even further than we might expect. Okay, here's another example. Now, in this case, they didn't give us the relative hydrogens, right? And so I'm going to need to calculate that, right? So I'm going to divide each one of these by 13.6. And I get 1, 2, 6, and 3. Right, so I've got relatively 1 hydrogen, 2, 6, and 3. And I want to see, right, is this just the relative numbers, or is this the actual numbers of hydrogens that I have, right? So 1 plus 2 is 3, plus 3 is 6, plus 6 is 12, right? So not only are these the relative numbers of hydrogens, but these are also the exact numbers of hydrogens that I have. Okay, the next thing to check is the hydrogen deficiency index. And so if I take my carbons, 2 times 5 is 10 plus 2 is 12. So my hydrogen efficiency index is 0. So I don't have any double bonds or any rings in this compound. So if we take a look at our spectrum, let's see if we can identify what any of these other peaks are telling us. So the first thing that jumps out at me is I have a quartet with a relative number of hydrogens of 2 and a triplet with a relative number of 3. Right? So this is the signal that I'm looking for if I have an ethyl group. So these two peaks are most likely an isolated ethyl group. And then with a hydrogen efficiency index of 0, I've probably either got an OH or an ether. And this peak down here looks suspiciously like an OH. It's at about the right numbers of ppms, and there's one hydrogen. So I'm pretty sure this is my OH. And so I have 3 carbons and 6 hydrogens that are unaccounted for so far. And so this peak at 6 is my 6 remaining hydrogens. And I think the most likely way to get this with what I have left is if I have 2 methyl groups that aren't being split by anything. And so I've now accounted for 4 of my carbons, all of my hydrogens and oxygens. So I've got 1 carbon left that doesn't have any hydrogens on it. And so I think the way I would put all of this together is I've got my carbon with no hydrogens, right? And it's got the OH. It's got my ethyl group. And it's got the 2 methyl groups, right? So my 2 methyl groups accounts for this unsplit singlet with 6 hydrogens, right? Because both methyls are identical. They're attached to this carbon. It doesn't have any hydrogens, so it's not going to split anything. Then I've got my OH here, and then these 2 peaks correspond to my methyl group.